So we'll move on to writing equilibrium constant, and that's another way to find out if you have a weak or a strong acid. It's by calculating the equilibrium constant. And when you have an equilibrium constant for an acid-base reaction, or an acid dissociation reaction, we call that an acid dissociation constant. So let's look at the generic reaction of an acid when placed in water. HA is a gas. When placed in water, will be in equilibrium with the hydronium ion and the A minus ion. How we get this? It's because HA is the acid in this case, because it has that H first in the formula. So it will donate its proton to the water. When HA donates its proton to the water, you add H plus to H2O, and that becomes H3O plus. And HA without its H plus becomes A minus. The bond between HA becomes a lone pair, and then H plus leaves with a positive charge, so it leaves behind a negative charge. So we will write the equilibrium constant for this reaction. Remember, equilibrium constant are a concept we encountered in chapter 6. And so if you want to be reminded of the formula you need to use for that, go to page 1 of your yellow packet. In about the middle of the page to the left, you will see equilibrium constant. Kc equals concentration of product over concentration of reactant. Remember those brackets, squared brackets, mean concentration. So here we will write the Ka because it's an acid dissociation constant in this case, because this is an acid dissociation reaction. So we need the concentration of the product on top. So here product are on the right as always, and we will take H3O plus in brackets times the A minus in brackets. There is no exponent because the coefficient in front of H3O plus and A minus are 1. So you multiply them together and there is no exponent. Over, and then the concentration of the reactant goes under, and the reactant in this case is HA and H2O. However, you need to remember that we do not include liquids and solids in equilibrium constant. Their concentration is considered constant, and so it's not included in there. So in this case, it would be just the concentration of HA on the numerator. And again, HA has a coefficient of 1, so there is no exponent on that concentration. So as I said, this is called the acid dissociation constant, Ka. So we have the A in subscript to recall that it's an acid dissociation constant. And there are many values of Ka that you can find in tables, in chemistry dictionaries, if you will. Chemists have done experiments and calculated those values for each acids, because each acid has a Ka value and they are different for all of them. So now if we look at this expression, on top we have the product, and if we have a strong acid, it's an acid that completely dissociates. So you could say that the bottom arrow is not there and it's a complete reaction going from left to right. So you would have very large concentration of H3O plus and A minus, right? So the numerator of this equilibrium constant would be a large value. And in the denominator, the concentration of HA would be small because all of it is completely dissociated into the ions to the right. So that means our Ka has a large numerator and a small denominator, which means when you calculate Ka, it will be a very large value. And so this confirms that the stronger the acid, the larger the Ka value. That's how you can tell, if you have a strong acid or a weak acid. It's looking at its Ka value. And the larger it is, the stronger is the acid. It works the same way with bases. And so that's a generic reaction for the dissociation of a base. So when you place the base in water, the base is symbolized by B and its lone pair. When placed in water, it dissociates into OH minus and BH plus. How we So our base, B, with the lone pair, is a proton acceptor. And so that lone pair will bind to the H plus and accept it. And so when B binds to H plus, it becomes BH plus, because the H plus comes with a positive charge. And water here is acting as an acid and donated an H plus. So when you remove H plus from H2O, you have only one H left, and H plus leaves with a positive charge, and so it leaves behind a negative charge. And so you get OH minus. Again, you can verify that this is correct, because if you add H plus to OH minus, the plus and minus cancel, and you have two H's and one oxygen, which is water. So let's write the equilibrium constant for that reaction. Again, we need K. K is the concentration of the product over the concentration of the reactant. So on the right side, we have the product, and here we have OH minus times BH plus. Remember how these brackets means concentration in molarity. So it's the concentration of OH minus times the concentration of BH plus. There is no exponent because their coefficients are 1 over, and again this time the reactant is only B with its lone pair, because the water cannot be included in the equilibrium constant because it's a liquid. This is called the base dissociation constant, Kb, because it corresponds to the reaction of the dissociation of the base. And again, the stronger the base, the larger the Kb value. If we look at this formula again, you can see that if the product have a large concentration, which means the hydroxide ion and the BH plus ion, if they are in large concentration, the numerator will be a large value. Over the denominator, and if you have a strong base, the denominator, the base will be completely dissociated into its ions. So the concentration of the base will be very small. So a large numerator over a small denominator will result in a large Kb value. And so that confirms that the stronger the base, the larger the Kb value. So this is practice problem number 6 in your list of practice problems found in chapter 9. So again, I will let you pause now so that you can do that on your own before looking at the answers. So what is the acid dissociation constant for the following reaction? If the equilibrium concentrations of product and reactant are the following. So you're given concentrations of HCN, Cn minus, and H3O plus. The equilibrium equation is given there. HCN, hydrocyanic acid, when placed in water, will dissociate into the cyanide ion, Cn minus. And so that's because HCN donates its proton to water. So HCN minus, the H plus becomes Cn minus. And then H2O accepts the proton as a base and becomes H3O plus. So first we need to write the equilibrium constant, write the formula for that. And again, it's the concentration of product over the concentration of reactant. Here the products are Cn minus and H3O plus. So you will multiply them on top of the equilibrium constant expression. So they are not raised to any power because their coefficient are 1 for both of them. Over the concentration of the reactant, and here again, water is a liquid and is not included in the equilibrium constant, so it's only HCN, the concentration of HCN in the denominator. Next, you plug in the values for each concentration, and so Cn minus and H3O plus have the same value, 4.9 10 to the negative 5 times 4.9 10 to the negative 5 over the concentration of HCN is 5. You do this on your calculator. So using the TI30X2S calculator, you do 4.9 second EE key minus 5 and times 4.9 second EE key minus 5 divided by 5. And sorry, I should have done that earlier. Times 4.9 divided by 5. The calculator answer is 4.802. 4.802 times 10 to the 10. So here you have to think about sig figs as always, and the concentration of the hydrocyanic acid is 5, and it's only 1 digit, 1 sig fig, so you need to keep 1 sig fig. So the 4.802 will be rounded to 5 because you keep the 4, but what comes after is an 8, so you round up, and so it's 5 times 10 to the negative 10. We didn't say that earlier, but there is no unit for K. K is a unitless value. Sorry. So now we need to decide if we have a strong acid or a weak acid. And earlier we learned that the stronger the acid, the larger the Ka value. So here, 5 10 to the negative 10 is a very small value, right? When you have a negative exponent, it's like dividing 5 10 times by 10. So that's a very small number. So our Ka value is very, very small. So it's the contrary of being large, which means we have a weak acid. So the Ka is very, very small. So the equilibrium is favoring the reactant because we have a weak acid, right? And it's mostly undissociated. If you look at the Ka expression, you can retrieve that. If you look that it's the hydronium ion concentration times the cyanide ion over the HCN concentration. If it's a very small value, you can see that means your numerator is small and your denominator is large. And that confirms that you have a weak acid because it means it's mostly, the equilibrium is mostly to the left, which means you have a lot of undissociated acid, HCN, which is neutral and makes it a weak electrolyte. And so a weak electrolyte is a weak acid. You can also verify that by looking at the concentrations. If you look at the concentration of HCN, it's 5 molar. It's a very large value compared to the cyanide ion and the hydronium ion. They both have 4.9 10 to the negative 5. 10 to the negative 5 is a small value, right? So that confirms that on the right side you have small concentrations, and on the left side of the arrow you have a large concentration. And so your acid is not dissociating very much, and it's a weak acid.